Last time I spoke at a conference like this, somebody came up onto the stage to introduce me, having already put my papers on the lectern, as Stuart has done here. And when the guy walked away from the stage and I came up to the lectern, he took my papers with him. That's right, I'm not going to do that, Stuart. So we're into the last session for today, so we're going to run through till a little bit after 6, about 6:15. And then we have some fun and games tonight with the dinner. This is a bit of an update on research and sort of R&D generally focused. The second half of the session, Jez is basically going to take the chair, who's known to you all, I'm sure. I'm going to be talking about some of the work he's been doing through Acquia. But firstly, I'd like to introduce Stuart Trow, who is a consultant now. He's changed his role so many times, I've always got to look at what the latest one is with HWM in Venue. I think you and I go back to the 1980s, Stuart, and all of this stuff, don't we? To the Report 26 from WRC and the Managing Leakage suite of reports and so on. So it's a great pleasure to introduce Stuart, who's been doing a really powerful, potentially, piece of research on background leakage. Stuart.
Thanks, Bob. So Ian mentioned the Managing Leakage reports from 1994. I sat on the steering committee of the group that produced those reports, the National Leakage Initiative that ran from 1990 through to 1994. And we had a lot of data from DMAs around the UK, and we were trying to make sense of what we were looking at. And Alan Lambert, who was on the group, kept referring to this fable or the analogy of the 5 blind men and the elephant, because different people were seeing different things in the data. Alan then came up with the burst and background estimates concept. I was there the night that he had this eureka moment. So we have reported bursts and leaks come to the surface, don't run for very long. We have the unreported bursts and leaks that you go out and find with active leakage control. And then below that, we have background leakage. And this is my picture of background leakage in a rural area. Basically, it's what you're left with after you've accounted for the other 2 elements. The other way of looking at it is, I've used this iceberg analogy before. Reported leakage above the surface, unreported leakage below the surface, and then background leakage being the deep dive. But there are various definitions of background leakage. You can see the one that's referred to in the Water UK route map have been the level of leakage that cannot be reduced further using current detection technology. What we focused on in this project that I'm going to talk about is the minimum achieved level of leakage in DMAs. That's the historic minimum achieved level of leakage in the DMAs, and effectively it's what a normal leakage detection suite doesn't pick up. The question we're trying to answer in the project is, can we reduce background leakage? The current definition just accepts that it's there, it's made up of a lot of small leaks, and we can't reduce it unless we do pressure management or mains replacement. What I've shown this slide before, we're trying to say, is that MAL level of leakage in a DMA, is some of it not leakage at all, but due to these other components? And if it is leakage, is it undetectable background leakage in the red box, or is some of it in the green box, the hidden detectable leaks? So that's the question. The project aims to redefine this MAL level by trying to locate and then repair those long-running hidden leaks in the DMAs. It's led by Welsh Water with support from 4 other water companies. It's a £3.5 million project, 2.4 million of which I think, according to Ian's slide, is funded from Ofwat. The rest is from the water companies and from other aspects. And then the contractors are HWM in Venio and also the University of Sheffield. We're selecting DMAs between 500 and 900 properties. We're installing multiple sensors of different types. We're then creating a digital twin model of that DMA. We're using that model to localize leaks, and then we're trying to locate the leaks. We started in late 2022, And the first thing we did was to look at data from the companies. I'm not going to go into the detailed contents of this report, but it is available publicly through that Figshare link on the University of Sheffield website. The key thing, we found that half of the reported level of leakage is due to the MAL levels in DMAs. So that's an important number to recognise. The DMA surveys that we've started, we have Phase B and Phase C. Phase B, we've done 10 DMAs and we've completed the surveys of those 10 DMAs. We produce an all-connections model of the DMA. We're not grouping demand to nodes in the DMA. Each connection in the DMA is a node. We've got consumption profiles for each node, for each connection at 1 minute resolution based on our stopwatch temperature logger data and other data modelled by University of Sheffield for where we can't get a logger on. We're also now starting to review paradigm data from SME for all of the DMAs. We're fitting pressure loggers to every available hydrant, between 20 and 25 per DMA at 15-minute values. We're doing transient logging with a newly developed logger from HWM. We're installing acoustic loggers at high density, and then we're combining all those data sets. So the first thing we do is we do a flow balance. So the top line on this upper graph is the DMA inflow. The green line is how much we're estimating is going past the customer's stop taps. So that's in terms of use events and customer side leakage. The difference is we're calling it unaccounted for water. It's been reported as leakage, but we can now see that not all of it is leakage. But you can see here we've got about 2 litres a second on average over that time period of a difference between what goes into the DMA and what goes past the customer's stop taps. We're finding on the customer side leaks that we're detecting with stopwatch a big difference between one DMA and another. These are, the top part of this graph shows the 10 DMAs. The bottom left corner shows that in one DMA we have no leaks, no customer side leaks. But on other areas you can see we have significant numbers of leaks. And overall we have 10 large leaks. We're classing a large leak as anything above 160 litres an hour. The Tier 1 and Tier 2. Tier 1 is our algorithm saying there's 87%, we're more than 87% confident that that is a leak. Tier 2 is more than 63% confident. So, you know, we're pretty sure these are leaks. And when the water company does a follow-up, we're finding that those leaks are largely internal with some external leaks. I've tried to collate all of this information into this table, which obviously there's a lot to take in here in the time that I have available. But if we look at the totals and the averages near the bottom, we can see that of the water that's going into the DMAs, 50% of it is leakage or unaccounted for water on the water company network, mains and comm pipes. 30% of it is customer side, and 20% of it is night use within the DMA. So those are ballpark figures, but you can see in the right-hand column how variable that figure is. So the variation in network leakage as a percentage of the minimum night flow is from 0, in other words, there's no leakage on the water company network, to 89% of what goes into that DMA is on the network somewhere. I would like to go into this in detail, but I don't have the time, but no doubt I'll get questions on it. I've tried to show this graphically. So the green bar is the network leakage as a percentage of the minimum night flow, and you can see I've ranked them from least, in other words 0, through to the most. So we've got probably 3 DMAs that have 10% or less of the night flow being leakage on the network, and at the other extreme we have 4 DMAs where more than 60% of the minimum night flow is accounted for by leakage on the network. So the work that the University of Sheffield is doing, the hydraulic analysis, they've developed a new technique of looking at pairs of loggers and comparing day and night values and then simulating leaks in the network. Where we have red points in the model, that is indicating that there's a leak. What they do is they simulate a leak and move that around the network, and where they get the best fit, that indicates the area of the network. So this is indicating there's some leakage in the top left of the network. They've then developed new techniques on the acoustics. We've got a PhD student working on the project full-time. We're not just relying on the alarms from the loggers, we're actually recording and analysing the acoustic data from the loggers. I can't go into the detail, but where we see these red dots in the top right of these graphs, that is indicating a leak at that point in the network, which isn't being picked up on the alarms from the loggers. Again, not a lot of time to cover this, but I've tried to summarise where we stand with each of the 10 areas. And if you look at the column marked network leak, yes or no, you can see that there are 3 DMAs where we're saying there's no leakage on the network. But then there are 3, 4, 5, 6 where we're saying, yes, there is a leakage on the network, and all the data is telling us that we should be able to find it. When I say leak, there's at least one of those DMAs where we're pretty sure it isn't a leak. It is water going somewhere else. It's too big. The amount of water is too big for it to be a leak that we can't find. It must be something else in the network. We're also going back to some of the first DMAs using the techniques that we've developed to see will these new techniques help us to identify where that leakage is occurring. But I just think, that's quite illuminating. So what learnings have we got? Well, the first box on here I showed last year. What we're saying is it's highly unlikely that background leakage is due entirely to small leaks below the detectable threshold as defined in the managing leakage reports. All the information that we're getting is suggesting that isn't the case. We're not saying that there aren't any small leaks, we're just saying that doesn't explain the whole of background leakage. It's more likely that minimum achieved level is due to a combination of detectable leaks, errors in the flow measurements, errors in the leakage estimation process. What we're also saying is customer-side leakage account for 30% of the minimum night flow. If we take one of the areas with the highest level of network leakage out, it's 36%. Customer-side leaks may not be detected using acoustic methods alone. We've got various examples where we pick up a leak with stopwatch, which you can't hear on the stop tap. It just doesn't make enough noise to transmit to the stop tap. Thorough company follow-ups are required on those points of interest on the company side. The average values that you have for night use and plumbing loss do not apply at the DMA level. There's just too much variability, not just in night use, but also in plumbing loss. So if you have an average plumbing loss value of 1.4, which was the UCWI report that we did a few years ago, if you apply that 1.4 to every DMA, you could be misleading yourself. You can have DMAs that have a very low level of plumbing loss, which we've seen in a smart metered area in one of the water companies, and then you've got areas which have a high level of plumbing loss. We're also saying that it does seem possible to localize these network leaks in the majority of DMAs where we're convinced there is something. And then in other DMAs, the mal is either due to customer use or customer-side leakage. Last slide, probably pleased to know. Where do we stand? We've got to follow up the actions in 4 or 5 of the 10 Phase B DMAs. We're on with the Phase C DMAs. We've done 5, we have to do the rest. Phase D of the project is an uncertainty analysis, which we've brought Steve Toombs back into the team to help with that. We need to consult more with the industry, and I'd appeal for people to get in touch with us with any stories or any sort of ideas that they have. Phase E is the reporting stage, and we need to disseminate the results, and we've had some support from Arup on that. I started with an elephant. I'm going to finish with an elephant. Background leakage. If we're going to half leakage by 2050, but half of that leakage is background leakage, how do we do that? Thanks.
Thanks very much, Stuart. We've got time for a few questions, so get your thinking caps on. We've got one question from the floor here, Stuart. When do we expect to see the final results and these results being in a position to be actionable and usable?
The aim is for me to come back to this conference next year and present on the full 25 DMAs and give the evidence behind that, and I'll need more than 10 or 15 minutes, Judith, to do that. We're also going to have this dissemination event, which will probably, I think there are two. One is combined with other projects, and then there will be a one just for this project, probably in the spring of 2026.
Okay. Any questions from the floor at all? Oh, we have one down here. Say who you are.
Michael Mott, Severn Trent Water. So this kind of also builds on what we had in the last session. So we talk about water going past the supply pipe, and it's not always clear, or past the property boundary, not always clear whether it's inside or outside.
Yep.
Is a better way to have a target for water reduction, whether it be PCC, whether it be leakage? Because at the end of the day, we want to keep water in the aquifers, water in the rivers. It doesn't really matter whether we save it inside or outside the house, but we do get very excited about whether it's inside or outside the house for regulatory purposes. Just wondering what your thoughts are based on what you've seen, Stuart.
No, I agree, Michael. We can tell how much water is going past the customer stop tap, whether we have a smart meter on there or we use our stopwatch device. We then need to follow that up to determine whether it's internal or external. We've seen a big variation in the size of internal leaks. We see ones of just sort of 10 litres an hour, or we can go down to 1 litre an hour. At the other extreme, we've seen internal leaks of 700 litres an hour. And when we see that, we assume, oh, that must be on the supply pipe. But we've seen internal leaks of over 700 litres an hour. I agree. We just need to understand that it is customer side, and we need to engage with the customer to do something about it.
I think on that particular topic, it might be the home insurance industry that we need to address. I think some insurance companies now insist on you having these below sink leak detection devices. There are a number of them around before they'll insure, so that could be a development. Right, a couple more questions here. Is there a correlation between the type and age of network or ground material and the level of leakage that the project has found in each DMA?
No. In simple terms, we've looked at that, and no, it seems to be completely random. There does seem to be an urban-rural split. It's more likely to have these hidden leaks in rural areas than urban areas, but that's not always the case.
And one more here, which kind of links to Ian's conversation earlier. With so much suspected losses deemed to be on customer supplies, isn't it now time to separate reported company leakage into network and customer responsibility? How do you stand on that one?
My view is that if the leak is beyond the customer's boundary and the customer owns that pipe, I don't see why the water company should be held accountable for it.
I'm sure there's plenty of views on that. Any other views on the floor? My own view, for what it's worth, is that we should certainly be reporting those numbers separately and then adding them together. But the support that we should provide to customers, particularly in vulnerable situations, should remain or possibly increase. Because I think it's all part of our education process. A lot of people out there, most people out there, I would say, don't understand where we are with the water resources challenges that we have in this country. And here is an amazing opportunity to change that, not just by fixing those leaks, but by educating at the same time. Okay, join me in giving Stuart a round of applause for his session. Well done, Stuart. Thank you. So, I'm going to welcome to the stage now to talk about another important topic and an update on another Ofwat funded project, which is around pipelining, which was very popular in our industry maybe 20, 25 years ago, mainly for water quality reasons, but it's about 50% cheaper than traditional methods, so potentially could deliver a lot. So I'd like you to welcome Dr. Katrina Flavelle, Innovation Technical Specialist from Yorkshire Water, and Joe Sanders, Dr. Joe Sanders, Senior Technical Director from Tetra Tech RPS.
So thank you. It's a real privilege to be back here and talking to all of you today. We've updated you a couple of times on this project, so thank you for the opportunity. It's worth saying that the slides today were prepared by one of the Institute of Water Rising Stars, Rob Bates, so thank you very much for that. bit of a double act between me and Joe today, so we'll pass back and forth. So I'm here to talk to you about Design Aligner. I'm going to aim to cover the AMP7 and AMP8 clean water lining landscape. Where are we? An overview of Design Aligner to date, including some great technical updates that are really hot off the press, and what's next. And what I really want you to take away from this presentation is that we have scope for more lining work to deliver our AMP8 plans and beyond. We just keep digging holes and replacing pipes. We cannot afford that, and we have to think about rehab. And that Design Aligner, I hope we can show you today, is starting to support that need and reinvigorate some of the lining sector. So a bit of an overview of the project. Why are we doing this work? So we started off with an UPWID project. We've had phase 1 of the Ofwat Innovation Fund project. We're now on to phase 2. To date, the project has had about £3.6 million of investment in total. There are a couple of challenges we needed to address with lining. Regulation in this country around lining is really stringent. Suppliers, installers, water companies said that is really hampering innovation, and they were not going to invest unless somebody did something differently. So an ideal project for the Innovation Fund to look at both asset lifespan, but also, as Ian sort of spoke about earlier, leakage as well. Testing, people said, I'm not confident in liners. I don't know it has a long enough lifespan. Is it going to deliver what it's needed? A bit about the ambition. Manufacturers and installers said, I'm not willing to invest in the UK. I see no ambition here, so we need to reignite that. And people were very uncertain about the cost of lining. And this was an opportunity to use some sector funding to do that. So as I've said, we've been funded by the Ofwat Innovation Fund, which is fantastic. The overarching aim of this project is to develop a new lining solution and route to market. We want this lining solution to be fit for the 21st century. We are not knocking what is on the market, but we think we need to do better. So we're looking for something that has an assured lifespan that will really deliver the financial benefit that you need in order to invest in lining. We clearly want less disruption by a no-dig solution. We're looking at additional benefits. So we've just completed some work to understand which additional benefits should we look at incorporating into a liner. It is that assured lifespan, but it's also looking at healable materials, not self-healing pipes, subtly different as the University of Bristol has educated me on. But if your lining solution fails over time, could we introduce a heat pig or a UV pig to go in and repair that material? And we think that's possible. Obviously, we'd like it to deliver environmental benefits, and it clearly needs to be cost-effective. So they're our key focuses for the project. Our solution, ultimately, we are not the owners as a project team of this lining solution. It is the market that will have to deliver it. So we are looking to work with suppliers who already have all of that lining expertise to take a product that they probably already own and know well, and to support them to develop that into what we've outlined here. We are not reinventing the wheel. So in terms of partners, we've had fantastic engagement from water companies. What we haven't had is someone who's just signed a piece of paper and walked off. If you're in this room and have contributed to this project, it's your technical expertise that has really made this project fly. Because we have some partners in this project that are not traditionally in the water sector. So we have the National Composites Centre, and for Bristol University, the Bristol Composites Institute. They have required a lot of upskilling, but it's really exciting to bring new entrants in because that's where we get the innovation. We spoke this afternoon, about it's great if you've been here for many years and you bring loads of expertise to this conference. But I'm really excited if you haven't been here long, because I think it's really interesting to have come from a different sector and be delivering something new to leakage and water. So they're really fantastic partners. But to support them, we have domain expertise from WRC and Tetra Tech RPS, and that's been a really great relationship to maintain. We're now at the point in the project where we can start to look for those lining industry partners, and we have had manufacturers knocking on our door saying, can we get involved? And we've had to say, no, not yet. Because the point of this project is to really design a lining solution that water companies want and need, not that a lining manufacturer thinks that we need. So it's important for us to own that design process. And Joe will talk a little bit about that and sort of the decisions we've started to make so that we ensure we get a lining solution that's right for us, not one that's simply delivered to us.
Thanks, Katrina. So the lining landscape, as we see it at the moment, you're all aware, well, hopefully you're all aware, those of you that are in water companies, that your business plans have all got a significant increase in the amounts of mains renewals you'll be doing. However, if you look at what the PR19 planned renewal percentage was, 2.07, and what the planned PR24 percentage is, you'll see there's not that much difference. However, actual performance at 0.64 suggests that we've got a long way to go. So we need to do things subtly differently. £2.3 billion will be spent on mains renewals in the next 5 years. Averaged at £277 per metre, thanks to Ian's sort of colleagues. However, when we've looked at it, we think that sort of the lining solutions will be around £175 a metre, which means that there's a potential just AMP8 savings of £907 million. Think of all the things that we could do with that 907 million. We could do X amount more kilometres, we could do lots more sort of PRVs potentially, we could do sort of a leakage review potentially, Ian, in that respect. So there's lots of potential things that we could sort of do with that money. And again, this is £3.4 million of expenditure, which we think is going to pay back 907 million in a 5-year period. That's a pretty good payback in anyone's book. So where have we got to? Fundamentals, and again, this is where we have all been taken back to school by the guys at the NCC, which is fantastic, about how do you actually go about doing these sort of projects. These guys do these sort of projects for some people that you might have heard of, Formula One teams, the British cycling guys, and again, I will say, as I said previously, if you ever get a spare sort of few minutes and you're in the Bristol area, then give Keris a ring and get a site visit because, oh my God, it is geek fest of the stuff that these guys do. The sort of the big spinner that they can sort of weave stuff with, all of the sort of stuff where they're like, oh yeah, you can't look in there. That bit's top secret. Can't look in there. Can't look over here. That bit's top secret. You can look over here though. We're doing smaller stuff that you can look over here. But all of these things where they're looking at how they can manufacture a wing in it. Is it 30 seconds, I think, for the full layup, something like that, Keris? Yep. They're not there yet, but they're looking to do it in 30 seconds rather than in sort of like 20 hours that it is at the moment. A full wing for a full aircraft, like mind-boggling side of stuff. But one of the things that they've sort of said to us is that you need to have this design intent document. What is it that you're actually aiming for? And we were like going, well, we've got that. We want a liner that lasts a long, long time and doesn't leak and all of this stuff. And they're like, yeah, you've got to be a little bit more specific about this sort of stuff. So we've had to go through a load of load cases, do the material analysis, and then that's allowed us to get to sort of structural model type approach that we're looking at. And again, this is some of the work that the NCC presented to the group just a couple of weeks ago. So the other thing that we need to sort of do is how we're going to test all of these things. And again, there's lots of different standards, lots of different tests that need to be done, both mechanical and chemical, so that we can sort of prove all of these things that are in the design intent. So they're from sort of like stress testing, all of the sort of impact testing, the leach testing that we've got there, and then the thing in the corner, like probably only 2 or 3 people will recognise, is a differential scanning calorimeter, which tells you how stable your polymer is. That's the thing that I used in my PhD for like loads, so I had to get a picture of that in. But these are the sort of things that we need to sort of like look at and understand how they're going to sort of make the material better. But also we've got the material science bit that comes in, and this is the bit where in all the hair shampoo adverts of old, they go, and this is the science bit, and some boffin sort of explains the science bit. We don't have time to go into the full science today, unfortunately. But the one thing that we need to do is that we're looking to evolve these materials. We've got lots of different additives that have been used in many different sort of things, from, again, the sort of looking at the boats that were used for the America's Cup, the sort of the way that people have been looking at structures for fins in propellers and that type of stuff that have got this toughening and healing sort of properties. And again, the thermo-reversible, photo-reversible sort of way that, i.e., as Katrina said, we could put a pig down that sort of heats it up slightly, or even sort of like puts a bit of UV light, and all of these micro cracks that we get at the moment in polymers would start to sort of heal themselves, not technically self-healing, but for everyone here, heal themselves. We also need to understand what the matrix and the fibres and how they're going to interact as well. And again, this is where we get the sort of the guys from the BCCI. We've got 2 fantastic postdocs working on these and understanding how they're going to sort of work through. The thing is, we can't just sort of go to a sort of a manufacturer and go, can we have a load of your product so that we can test it for a while? But what we are doing is using bulk polymer products that are available sort of readily off the shelves from anywhere and understand how these additives impact these polymers. This will give us a starting point to then go and sort of do that full piece with the lining manufacturers and say, based on this, which is very similar to your polymer that you've got, it has done this. It has increased the lifespan by X amount. It's been able to self-heal. We've done this. One of the things that the BCCI think that might be possible is that actually just from this sort of the thermal transfers between the water has between summer and winter, that might be enough heat to sort of like close these cracks. Now this might be a point where actually we don't have to send anything down. Now wouldn't that be fantastic? This pipe just sort of improves itself. So the water, again, polyethylene is very much degraded by water, will sort of run out as the Upware project showed. But some of this stuff now, potentially if you add something else into it, the water then starts healing itself. Fantastic. So that's the progress of where we are now. I'm going to hand back to Katrina just to sort of sum everything up and look for the timelines of where we are going forward.
Thanks. Yeah, so as we enter 2025, as I said, we're looking to identify partners to work with, but really importantly is looking at that cost-benefit analysis, because there is no point developing a shiny thing unless it pays back. It's not what we do in innovation, it must pay for itself. So RPS Tetra Tech has started to do some of that work with the support of WRC. And then towards the end of the year, we will really wrap up the mechanical and design testing and the material and process quantification. As we look further ahead, we need to demonstrate and exploit this, whatever solution we have. But I just want to flag a project risk to you. Reg 31. Anything you put in our clean water network has to meet the standards set out by Reg 31. That is a real challenge for lining manufacturers in the UK. If you've spoken to a lining manufacturer recently, they will talk your ear off about the challenges they have getting their product approved. We've recognised this in this project, and as a result, we are going to get the product that we develop ready for Reg 31 approval, but we're ultimately not going to take it through. In terms of dissemination and engagement, we have our first phase 2, which is a bit of an oddity, but phase 2, our first paper, is now available on Spring if you're interested in what we're doing. And I want to show the photograph here because I think most people in this room will identify that they know at least one person in that photograph. And this is just a fraction of this project team that are developing this solution. And I want to say that this is, I think, one of Jez's questions earlier on Slido is, should we collaborate more? I'm not sure on this project how we could collaborate more at this point because we have such a fantastic group of talented people contributing towards it. But we're always looking for more. If you'd like to come and join, let me know. So I hope that I've shown you with Joe that we have scope for more lining work to deliver AMP8 plans and beyond, and that we're working to support this with Design Aligner. I'm here for dinner and the next day, and Joe is obviously too. We'd welcome informal discussions with you if you'd like to know more about the project. Thank you very much.
Okay, we've got time, a few minutes for a couple of questions from the floor. Nothing much coming up on Slido. Anybody got any questions they'd like to ask about this? It's a hot topic, an important topic. Just think of all those cost savings.
Ian's already put them in the budget.
Oh, Jez. Thank you, Jez. Put your hand up. No, put your hand up again, and the microphone is right down the front here.
Just wait for a second.
Just wait for a second, Jez, yeah. Hard for you, I know.
So, no, thank you. Really interesting. One of the issues, obviously, with lining technology is your tappings and how are you going to incorporate tappings and how you deal with that, particularly in urban situations where you're going to have to drill down on those. What's the thinking on that at the moment?
So it's one of the design cases that we've already put into the sort of there. And again, we're still not at the stage where we know exactly what the design of the liner sort of structure will look like. Again, what the sort of the matrix might look like. Will it be a sort of a CIPP style, or will it be a spray type sort of liner? And again, depending on where we go, and again, more and more a hybrid solution between those two looks like the way that it will be going. That then sort of allows us to sort of make that easier. But one of the things that it does have to do is that you don't need basically sort of a diamond cutter to be able to cut it to then go and do the tapping. So it's one of these things where it's making it strong enough to withstand the stuff we want it to withstand, but not strong enough that it's undestructible when it comes to tapping and that type of thing. But yeah, that's one of the low cases that, again, we are getting a smaller and smaller sort of design window. And again, sort of 2 hours of discussion a couple of weeks ago on how small we can actually make that and actually hit it because of all these different design scenarios that we might need in the future.
And there's another question down the front here from Joe.
If you had involved any trenchless contractors to get their views and input, as one hopes that there'll be loads of them beating a path to your door in due course.
Yep, we've gone to UK STT. I presented at UK STT 6 months ago. Got a much frostier reception than I did this afternoon, I have to say. It was not exactly the best news to a lot of them. That what they'd done was fantastic, but we needed the next step to go forward. I think there is also engagement through Steve from WRC. He's obviously sort of well aware of those contractors. We've been talking to them. One of the things that we sort of set ourselves as a challenge is, can we use the equipment that's already available? So not reinvent a sort of a new way of installing it, but it might need a new way or an involved way of installing it. So again, we're definitely engaging with those contractors. And again, those will be part of the sort of the further engagement as Katrina talks about going forward.
We've got Alex Spivey from Yorkshire Water talking tomorrow, and he's chair of the expert in situ lining group. So great to have their engagement to understand what we need to be doing and who we need to be contacting.
Okay, we've got time for one more question. We've got one right in the corner over the far side, and she's got a microphone already. Go ahead. Who are you?
Came with my own. Tanya Daly from Dayworth Consulting. I just wondered how you pick out a good target sort of candidate main for lining. Are there any condition assessment technologies that are really preferable for that sort of experience?
We've gone more down a statistical route using, and I think someone's talking about the mains failure database tomorrow. So we've used information from that. What are the main sort of criteria that are of those that are sort of coming to end of life, and designing for those rather than sort of going, right, okay, we need a particular way of understanding which ones we are going to replace at this stage. We're just sort of doing that strategic, what material sort of size combination do we need to hit to make sure that it's got the biggest market possible. And again, talking about things like, well, would it go underneath railways? Well, I don't think anyone in the room that works for a water company would feel particularly pleased just lining underneath the railway. They'd probably want a proper sort of replacement at that stage. So again, that's the sort of thing that we can discount fairly quickly. Making sure that condition assessment is right in the future, yeah. But again, it might be that we just have to line everything because it's actually more expensive to do that condition assessment rather than just doing the lining. So again, all of these things are possible.
Okay, I think we'll call the Q&A to a close there. So please join me in thanking Joe and Katrina. Thank you. Well done. Okay, so now we're going to talk about the universal access point for water, and I'd like to introduce Dr. Leo Carswell, who's Head of Technology at WRC, and he's been working with Jez on this project. Welcome, Leo.
Thank you, Bob, and good afternoon, everybody. Good, so I'm going to talk about another Ofwat innovation project. This one's a little bit smaller than the others you've heard from. Shorter project. We've actually completed this project. I'm going to talk through the journey we've been through, a journey, and it's all about developing a technology, for access into water mains. And you can think of it as an enabling technology. Lots of the things we've talked about today have been about solutions to leakage. This is an enabler to allow you to solve the problem of leakage. Lots of logos up there. This project was led by, and is the brains behind it is Jez Heath. So Jez set this up. 5 water companies involved in steering this. WRC and Fluid Consulting delivering that with some help from University of Sheffield as well. So like all of these, big collaboration. You'll hear me talk a lot through this about stakeholder engagement. And by that I mean the supply chain, academia, supply chain we're engaging with at the moment, supply chain who don't work in the water industry, contractors who are feet on the ground digging holes, but also contractors developing technology and new innovations. So very broad range of people involved in this project. So why a UAP? Well, the main driver is that there is a need to understand our water networks better. We need to understand the condition of them better. We need to be able to detect leaks better. And we've started the conversation talking about we need to be able to repair them without digging holes. That requires better access into our networks. There's technologies for those type of activities already available, but the access into the network at the minute is a limiting factor. And there are access points already available that you're all using. There are hydrants, there are tapping tees, there are bespoke fittings, but none of those actually provide ultimately what we really need for those types of technologies. They all have some limitations. So this project was about designing. We haven't built anything in this project at all. It's about designing a new type of access point. A key point with this project, which differentiates it from a lot of others, is that it's completely free IP. So all the ideas that have been put in and developed with this project are not owned by any individual or the project. They are being made available to whoever wants to take this forward. We are removing that barrier of IP, which stifles innovation some of the time. So I'm going to talk a little bit about challenges and vision and specification. I'm going to talk through this quite quickly, but it was a key part of the process that we went through. So we started off with some workshops on this project, again, with lots of stakeholders. And one of the things we asked at that first workshop was about, what's your vision for this universal access point, this so-called universal access point? And a number of key points there people were talking about. We'd love something that's just usable by the water companies. We don't have to worry about the fire service needing to use it. We can install it rapidly. We can install it optimistically. We can install it when we have an opportunity to install it. So we have a leak somewhere. At the same time as repairing that leak, why don't we put an access point on there? That way we're building up the potential to be able to survey our network. A key point that the stakeholders fed back to us, that don't get drawn into trying to make this universal access point do everything and be super complicated and have all the functionality. Create something that is suitable for the network, suitable for the industry, but supply chain, with their wisdom and their technology innovation, in the future can bolt onto this and add new things onto it, and it can evolve in the future. So that was a key point. We also challenged ourselves to look at the barriers and some of the challenges with this type of technology. And I think we recognise that developing new things in the water industry technology is quite challenging. We've heard already implementation and adoption of technology. We're getting better at it, but it's still very difficult in the water industry. It's a slow process. So we challenged ourselves to look at some of this and the sort of things that the stakeholders were talking about. You can imagine we're talking about putting a lot more access points into the water network to understand it better. People are immediately thinking, how does this, what's the risk in terms of water quality? We've got all these access points. How do we get water companies and manufacturers on board with this concept, this idea that you're developing? How do you turn this project into a product at the end? How do we remove the barrier of installing something into the network and the time that takes, and value installing that into the network. And we came up with a design specification. So, with all these stakeholders, academics, contractors, all chucking things in from different sides, we came up with a specification. 28 items, and some of the key points there. So, obviously it has to meet Regulation 31. We were talking about a 100 millimetre access point that you can put something in. So it's 100 millimetres, so it's larger than current access points, suitable for a range of different pipe materials, range from 80 mil upwards, so it's suitable for use within the distribution network. We've got access points on trunk mains. That isn't where the challenge is. The challenge is understanding the DMA better. And of course, managing maintenance and cost and things like that. So, I'll talk a little bit about the economics. It was mentioned in the last talk. No point in designing something if it's super expensive and super complicated, too expensive for the water industry to adopt. So we actually spent quite a lot of time understanding the use cases and the benefits for a UAP, and understanding the numbers of technologies that you might adopt. Therefore, positioning this so a technology supplier could take this forward afterwards. And I've summarised the whole report into one page, but the feedback from the water companies were UAPs could help us with pipe condition assessment, they could help with access for sensors and robotics, and they could help us with DMA leakage. They were the top use cases. And through some quite detailed modelling and analysis, we were able to look at the sort of numbers of these fittings that you could imagine the water industry may be installing in the future. And it's quite considerable. And I've put a very brief summary there, but between 70 and 370,000 units we could imagine. And these are quite conservative estimates based on specific information of our networks and those user cases and the benefits that they could deliver. It could be a much larger number. But the importance of this is that if someone is going to take on board the outputs from this project and develop a product which they're going to sell, they want to understand that there's a market there. And this is the foundations of understanding that market. So, talk a bit about the designs, because actually that's a lot of what we did. So, our objectives were to develop some design ideas based on the specification and to engage with a range of stakeholders and challenge those design ideas. So they weren't just WRC's ideas, they weren't just Jez Heath's ideas, they were ideas that had been challenged by the industry, by our sector. So we developed 4 ideas, four concepts, and I'm not going to talk about these 4 concepts here, but initially developed 4 very different ideas. They were taking the challenge that the specification set and interpreting them in different ways. And we took those to the stakeholder group, and we had a workshop where they assessed those and scored those against the specification. And these graphs, if you can only spot the red and the green, that's all you're meant to be able to see. We found that 2 of these aligned better with the specification, and the green shows where they align better with the specification, those individual items, and the red shows where they don't. So we had 2 ideas that the group thought were worthy of taking forward, and 2 ideas that probably weren't. Maybe they were too complicated. They couldn't quite see how they should be taken forward. So the next bit of the project was to refine those ideas, take those ideas further and closer to something that could then be adopted by supply chain. So there's 2 ideas that we took forward. So our objective within the project was just to refine it to 1 idea. But with all good research projects, things change as you go through, and we had 2 good ideas that complemented each other. They were different, so we said, well, why don't we take both of them through? That gives more options for the supply chain to look at by the end. So we've got 2 ideas here. The first one on the left, B, is a design that's based on a slot that's milled into the top of the pipe. It's a repair clamp with a milled slot and a ball valve that you can use to angle the access into the pipe so you can go upstream and downstream. The second design, much simpler, 90-degree design, but is focused on including an element which protects any technologies you put in from the cut edge that you would have from coring out a pipe when you do a live coring activity. So two different approaches, and I'll talk a little bit about those in a minute. First of all, partway through the project and in parallel, we looked at some slightly different technologies. These are live tapping these technologies which can be installed live, and they provide a stop valve, and they can be installed live. So these are technologies that are not a UAP, but they're quite interesting because they incorporate live milling or coring into the pipe. They actually incorporate live coring to the full diameter of the pipe. So you can imagine using some of this technology, you can actually get an equal T on a pipe. So on an 80 millimeter pipe, you can have an 80 millimeter connection onto that pipe, which is not what you can do using conventional saddles and technology. So quite interesting, and the applicability to this, it's a bit of an enabler to be able to evolve some of our other technologies. So I'll talk about the two designs very briefly. There's a huge amount of information that the project has produced, which is freely available, and I'll signpost that to you at the end. But this first design is Design C. This is all about protecting the cut edge, which you get when you do a live tapping. So this design utilises existing components. We've got an existing repair collar, an existing valve. The really interesting, clever bit is the bit that's actually sitting between the valve and between the repair collar. And this bit, this is the bit where the sleeve that goes down into the pipe is held, and also it has the potential to have tappings. So you could put a sensor on there, or you could do an air valve, air release valve. And this is all made with products that are already standard in the industry. They all have Reg 31 approval. They're all relatively low cost. So this was all moving towards that direction. The second technology, a little bit different, was around using, as I said, a ball valve. So this again uses a standard repair clamp. The concept with this one is that you could mill a slot along the crown of the pipe, going along the pipe, and use the ball valve to angle whether it's a tethered technology or not, angle the deployment of that upstream or downstream. And that gives you more control of the deployment. So. And my final slide, Bob, hopefully I've helped you catch up a little bit of time, maybe. So, yes, this project was all about developing concepts and ideas. It was not about building prototypes, building something that would be trialled. The expertise in all of those aspects in terms of prototyping, design for manufacture, design to be the right cost, the right materials, approvals, sits with the supply chain. And that's the next step for this project, is to take the ideas that we've developed here, and for the supply chain, number of suppliers, a single supplier, to take those without any IP restrictions and evolve and develop those to supply a solution back to the water industry. Finally, we've been engaging with Spring. There was a dissemination event back in October. The recording of that is available on the Spring website, and all of the outputs from the project will be as well. And Spring will be supporting the project going forward in terms of engaging with suppliers. That's it.
So I think we've got a couple of questions for Leo here. Firstly, with so much suspected losses deemed to be on customer supplies, no, that's not the one. Sorry, I did see one here. I can remember it actually. There was the concern was basically if we're going to be putting all of these devices onto our network to get better access, what does that do to our background leakage?
Yeah, you are creating more points in the network, aren't you? So I would say, obviously, there's a benefit. The whole concept of this is it gives you access to be able to monitor for leakage, to be able to detect that leakage anyway. just got to make sure the workmanship is right. Just got to make sure that when these are installed, that they aren't leakage points in themselves. And they are actually, they have the function that we're envisaging, that require, that they're a benefit to us, not a leakage point.
Okay, any questions from the floor for Leo? Oh, we've got one at the back there, in the corner. Hold your hand up, high. So just let us know who you are and where you go.
Thank you, first of all, Leo. It's Gary Table from Badger Meter. I have an interest in sensors in a network, as you well know. One of the questions I'd like to ask is where we take this from now with supply chain. In terms of leakage, the question is about leakage. How would you put a sensor in there and not create leakage? Because you're going to have a sample. Can we get the water back into the network without creating a leak? And have you looked at things like turbines, inline turbines, to generate power? So we can put all sorts of devices in there.
Yeah, the whole concept of this area is about a universal access point. So it's for the supply chain's imagination to run wild. So turbines, ways of getting water in and back out, sampling systems, sensors, that's for the supply chain to work out. We have tried to create something that enables that, rather than a hydrant that is on a leg through several bends, that's in the middle of the road, that's in a difficult, all those difficulties, trying to make it easier and have something which is designed for them with a water company in mind rather than the fire service.
Yeah, I don't think the market for sensors is going to go down. Quite the opposite, in fact. Any last questions for Leo? Well, perhaps you'll just join me in thanking Leo for his presentation. Well done. Yeah, I'll take your papers, thank you. So for this last section, I'm going to hand over to Jez, who's going to run this part of the day for the next hour or so, hour and a bit. So I think Jez is known to most, if not all of you, and I'll leave him to introduce himself and the three speakers who he will be managing. Over to you, Jez.
Thanks, Bob. It's really nice when you're looking at the photos there, because you suddenly realise how long this conference has been running, with some of the photos going way, way back, and you think, yeah, still had hair back then, occasionally. Right, some of you will have come across the Dunning-Kruger effect. Dunning-Kruger says, if you don't know a lot about something, you tend to overestimate how much you know or how simple it is. It is why people turn around and look at leakage and go, how hard can it be? It's just water running out of pipes. How difficult can it be to solve this? Why does this industry struggle? Because, come on, surely it's simple. But it's not. Dunning-Kruger says, actually, as you learn more and more, you reach a turning point where suddenly you come around the corner and you look up and you realise how much you still need to understand in order to be able to manage and work on that. We are at that point in this industry. It is why we've got an entire afternoon looking at innovation and research, because we now look around the corner and we go, oh my word, look at how much more we need to understand about our buried infrastructure, about how our customers use water, about our under-registration on our meters, about the material science that we're bringing in. There are so many areas that we still need to do research, that we still need to do innovation in. I've been in this industry over 30 years now. This is the most interesting times I've ever come across. Those of you who are coming into this industry now, congratulations. You've come in at just the right time, because this is fascinating. And those of you who are getting to my age and thinking you're going to be leaving soon, I promise you, you're going to struggle, because it's just getting exciting. Right, let's talk about the Aquia update and the research programs and everything that's going on there. So, as you've heard, I'm Jez from SES, is the easy way to remember who I am. SES Water, I'm the innovation manager there. But I'm also the program lead for Aquia. UCWIR, UK Water Industry Research. It's the body joint funded by all the industry that carries out research work. And this is my research programme. No, this is your research programme. And I say that because although this is funded by the water companies, each and every person in this room, if you are working in leakage, this is important to you. It's not just about what water companies are interested in. If you're a supplier, these are the problems we are trying to solve. This is where we need to go. So it is our research programme going forward. Blues, projects completed. Greens, live projects at the moment. Oranges, projects coming through. The other ones, ideas that we've had in the shower that we thought were a good idea. There's a load of work going on there. We are the busiest of the UCWIR programmes. We started well under Dennis Deller, and we've continued that momentum. We've done the Leakage Innovation Heat Map, published and available from the UCWIR website. There you go, yes, thank you for actually using the QR code. Wonderful, thank you for that. But that's available. This was basically born out of when I came into the industry, when I started doing this bit on UCWIR, somebody said, there's a lot of duplicated research. Okay, let's find out if it is. So I went and visited everybody. I said, share your research plans. Do you know what? We collaborate. Ian talked about that earlier. He said, look, you need to do collaboration. And I said, okay, how can we collaborate more? Because in my view, this group is one of the most collaborative in the industry. Leakage, water leakage is held up as being the exemplar of collaboration because we share. 400 water company projects, UCWIR projects, Ofwat funded projects, spring knowledge shares, all gathered together on one Excel spreadsheet where you can find out what's going on. Who's working on what? Well received, as I said, by water companies, suppliers, and regulators as well. But we recognise that it goes out of date. I did it originally in 2019, was the first time we did it. 2023, October, I did the same again. I'm going to say provisionally, 4 years' time, I'm going to be travelling around again and I'm going to do it again because it goes out of date. We need to keep it up to date. We need to understand what's going on. You can tell Doug, by the way, he knows. So what I also want to do is show you that how that works out into the various areas. So what I've done here is I've done the prevent, aware, locate and mend on the side, but I've done it in a slightly different order because what we've started to realise is that there is an innovation landscape. You know, when you look at the UCWIR projects, we know that our awareness side is pretty well mature. Everybody in their water company has got an awareness product at the moment that says, go and look for leakage in this area. Now, that's not to say that we won't see new solutions coming through. My own company adopted a new solution precisely in that area. But most of the research we're doing in that area is effectively going, who's doing it best? Okay, bit of comparator stuff. Everybody's got one. How do we just optimize this? So our UCWIR research tends to be at this kind of up at this end. Locate, you can see in there, is pretty wide. We've got stuff that's well developed and in situ. Acoustic networks that have been rolled out. And we've got brand new developing systems coming through like satellite, dark fibre and things like that. And people saying, okay, how do we do it best? But also, how do I actually install it? Prevent. It's got the widest breadth because over here we've got PRVs that we've been putting in for decades. Well understood. But at the far end on our prevention side, as you've been hearing today about network calming and pressure reduction, how do we manage that? How do we bring that in sensibly? So it has a really wide breadth for that one. And then finally, as you can see on mend. Okay, in terms of our UCWIR research, we're really at the fundamental state there of saying, what's the cost benefit? But that's only the UCWIR programme. When you look at the water company programmes, you can see that they fit out into far wider areas. Water companies are going all the way back to the fundamentals and going, yeah, UCWIR may be only looking at the best things, best practices here, but I've just seen a new supplier and I want to have a look at what they're doing. So we've got a really wide breadth there from the company side as well. Ofwat Innovation Fund takes you from mid-TRL levels up to it's almost BAU, late TRL levels and things like that. So we've got the Ofwat Innovation Fund projects coming through. It's interesting you mentioned there's 4. By my count, there's a lot more than 4. There are 4 that are specifically about leakage, but there's a number of other ones. Thank you. Number of other projects that impact upon leakage, say smart systems, UAP and things like that. All of these ones coming through as well. And then, of course, there's the Spring Knowledge Share as well, that effectively says, OK, when it's nearly ready to go to market or has been done in trials and is being rolled out, it starts to be shared on the Spring Knowledge Share. There is a wealth of information out there about what is going on within this industry. I was asked earlier today about where we sit in the UK as an industry in terms of our water leakage. Where do we sit internationally? I was talking to New Zealand. It's one of those things where you get up in the middle of the night to speak to New Zealand. I was talking with them, and they were astounded at the kind of innovations that we've got coming through in the UK. We are driving down leakage without the tool that almost every country uses or every city uses if you want to get it down really low, which is massive mains replacements. You go to Tokyo, they ripped out all their mains, they replaced the whole lot from the 1960s. Okay? You go to Germany and you say, how much cast iron have you got on the ground? And they just laugh at you and say, we got rid of all of that. They've all done massive mains replacements, and that's how they've driven their leakage levels down. We don't have that option. That is the last option on the table. We've been talking about it today, about how we manage that side, and we know that's going to come through. But how do we drive down leakage without doing that? And that is why the eyes of the world are on the UK at the moment. Because if we can do this, everybody will want to know how. Everybody will want to take these technologies and methods. Okay, Upqueer programme. As I said, 19 projects it is. I've done 18. I've got one which is just finishing and publishing out at the moment. We've had 4 dissemination events recently. What we tend to do with those is we schedule them in with the leakage managers. We sit down and we go through with them and we share all the learnings so that as we're doing those studies, it gets out there as well. Doug Spencer from Anglian, he is my co-programme lead. We attend every meetings of the leakage managers. It is important that we are there, getting feedback from what is happening in the industry at the moment. What are the key concerns? What are the priorities within that industry? And we ask the leakage managers to prioritise what we're doing. What we do is, literally, Doug and I will come up with a list of this is what we think we should be researching, this is what we think the priorities are. And we throw it out to that leakage managers group and we say, shoot us down. Tell us what you think the priorities are. And they come back and they tell us, and that's what we then start taking forward. So we understand and make sure that we are addressing the needs of this industry. What we know at the moment is there's still a dearth of live projects on MEND. Okay? So you can see the percentages there. About 52% of our leakage spend is on repairing that pipe. It's the area where we've got to put a lot more into. And you've seen all the other comments today about where we are. Despite all of this fantastic innovation, despite the eyes of the world being on us, we are still struggling. I was asked about this the other day and somebody said, hang on, wait a minute, you know, you're meant to be really good, you're meant to be doing so well, why are you guys struggling? 2 words, climate change. When we brought out all our plans and we said this is what's going to happen, this is how we're going to drive it down going forward, we knew about climate change. What we did not understand is how quickly it would affect our industry. I've been talking with the leakage managers, I attend their meetings. We know that 2-3 summers ago we had this massive breakout due to soil dryout, but we've seen it every summer since. Even in wet summers, we're now starting to see this soil dryout causing mass breakouts within our areas. Leakage managers are running scared of the effects of climate change upon their ability to drive leakage down. We're aware of that. Doug and I are adapting our research plan accordingly because we know this is going to be an increasing issue going forward. We've recently shared these ones, deep dive into leakage using smart meter data. This was a really interesting one. We looked at areas from Anglian where they had a high density of smart meters in an area, and we said, okay, can we therefore match it up? Can we actually do a balance on that DMA area? And the result was no. It's really hard, even with smart meter data, to do that balance. And the reason, one of the reasons behind it was the leakage data on customer side. Because your meter is recording consumption and you will not have that confidence at any 1 second to say, yes, that's consumption or that's leakage. Leakage tends to take us a number of days to become aware of on a customer side. But what that project did show is that if you get more than 30 or 40% meters within an area, your confidence in terms of sending the guys into that area massively increases. You're talking earlier, Stuart, you were talking about, okay, we have these areas where we don't know whether it's consumption, we don't know whether it's big leaks or whether it's small leaks. One of the big problems is you send your guys into a patch and say, go and repair, and then it drops all by itself. Once we start to bring that smart metering data in, it makes a big difference to our confidence in those areas. We say, actually, no, this is usage or it's leakage. Assessing the levels of leakage on new polyethylene networks. Sadly, it still occurs. We still have leakage on our PE. What that report found is that good workmanship, and it was interesting as soon as you talked about, okay, how do we install the UAPs on there? Workmanship is important, even more so on plastic. And making sure you get a really good pressure test, that you've got a good process in terms of dealing with that. And then finally, the impact of pressure transients. Had a Sheffield PhD demonstrating that and showing that, which was fascinating. He was here last year. He gave his final dissemination a couple of months ago. Fascinating to see, and really giving us a good understanding of how cast iron is deteriorating and going forward. So where are we going? I've got 4 projects which I'm now currently looking at, and these are going through the UCWA voting. So I'm going to tell you about them. I'm allowed to do this. I did check this. They're not actual live projects yet, but they're going to go through the voting. Factors affecting leak repair times. I want to understand what are the root causes of long-running leak repairs. Why do some repairs take weeks, months, or even longer to repair? Is it down to the process? Is it the councils? Is it something like that? Is it about that particular road? Or is it engineering difficulties? Is it the fact that we can't dig down that deep? Is it because it's going underneath a railway? Are there technical things that we could do to solve it? So we're going to start doing that. Calculating whole life costings and value of mains renewal methodologies. We've talked about replacing pipe. Okay, I want to know what the cost of replacing pipe is, and I don't mean the financial cost. Thames Water put up recently a cost for replacing 1 mile of pipe in Mile End Road, London. The budget cost for that was £20 million. 1 mile of pipe. Why? Because there's loads of other costs involved as well. But we also want to look at the social and the environmental and the carbon costs of these various methodologies, understand those, so that when we come to do mains renewal programs and when we have to ramp up, we've got the best understanding there. Understanding factors contributing to and affecting overall leakage. This is doing another way of trying to come up with that and going, okay, it was interesting, Stuart, the question to you, and then we were asked, was there any correlation with the mains type and materials? This is trying to build it from the other way down and going, okay, let's look at things like self-organising maps. And if we put all those data in, where's the weak and strong correlations in our DMAs? And then finally, defining a consistent approach to MAL, the minimal achieved leakage and the minimum achievable leakage, and we're looking at that as well. And saying, okay, can we come up with a consistent way of doing that, because that will help inform us again going into areas. There we go. That's it in terms of UCWA. I know I've got other bits to do, but let me pause there. Any questions on what I've said there as I rattle my way through my talk? Hello, the young man in the middle there.
Two things, Jez. On the Mal and Mabel, that was one of the things we had to do as part of the background leakage project. It was to understand what we meant by Mal and Mabel. So please talk to us before you define that.
Brilliant. The idea behind that one is actually coming up with a consistent approach. We know that people do Mal and Mabel. What we're looking at is going within our companies in the same way as we've done a consistent approach in terms of how we calculate leakage. Can we come up with a consistent approach amongst all of our companies using our data to actually calculate that ourselves consistently?
Yeah, we looked at different approaches and we suggested which one to use.
Fantastic.
So the results that we'll publish through the background leakage project will be based on the methodology that we put forward.
Fine. Good.
The other one is on the factors contributing to the overall level of DMA leakage. The phase D of the project that we're doing is looking at the uncertainty, and we're starting to wonder about calculating leakage at a DMA level when you take account of all the different components that go into that calculation. So again, please liaise with us.
Absolutely, we'll liaise. The point behind that one is, if I invented a fictional DMA, and I know you've kind of gone through the same approach, but if I gave you a fictional DMA and I said it's got this much cast iron in, it's this much pressure, it's got this many transients running through, it was laid in 1930s by Fred, who lived just down the corner, and he worked really well on Fridays, but Mondays was the bad day for him. What's the leakage in the area? Well, I have no blinking idea, because I don't know what the strong and weak correlations are. And that's why I want to use things like self-organising maps. We'll actually tease that out and go, okay, let's look at all of our data sets and go, where's the strong, where's the weak correlations? What makes a difference to leakage in our areas? And it may come back and go, we can't find any correlations whatsoever. But I'm hoping there's at least one or two out there. Okay, any other questions? Question at the back, young lady there. Hi, Katrina, do you want to just shout it? I can hear. Oh, that's true, okay. I was going to repeat it, but...
So, Katrina Flavel from the innovation team at Yorkshire Water. It's great what you're doing. In the next AMP, I think a lot of us are not going to be doing much on customer-side leakage, but UCWI's job is to look to the future, when inevitably this challenge is going to come round again. In the meetings that you attend, is there much call for sort of supply pipe leakage challenges? Are you thinking about it? Where does it fit in your sort of priority matrix?
Let me tell you, sorry, I love this moment, thank you. Let me tell you about the Croydon Group. You see, yeah, you knew where I was going with that one. Right, the Croydon Group is something you may have heard whispered in secret, people saying, I'm going to the Croydon Group. The Croydon Group is basically an industry group that we set up that is looking specifically at customer-side leakage, because 2 or 3 years back, I recognised that that was coming over the horizon. And where I got that from was from Anglian and Thames, because they were rolling out smart meters and they were seeing a 10-fold increase in the number of continuous flow alarms that they got back from their smart meters. 10 times the amount of customer contacts that you would be getting as a result of putting in smart meters. So therefore, as every other water company rolls out their smart metering program, they will come across exactly that same situation. So we were talking earlier, Bob, you were talking about how do we deal with customers? How are we going to deal with when we've got 10 times the amount of customers who have a leak upon their supply? Potentially a leak. I'm saying it's continuous flow, okay? But potentially a leak. How do we deal with that? And that's what the Croydon Group is looking at. It deals with it in 2 areas. Number one, it looks at policy and it says, okay, look, as water companies get more and more smart meters, almost inevitably they're going to have to change their policy about how they deal with them. So one part of that looks at the policy side, and then a second side says, but we will still need to repair them. Even if you have a policy that says we're not going to be doing all of them. Yeah, the policy change, you're going to have to change how you're doing it and deal with your vulnerable customers. And say the vulnerable customers are going to be the ones that we're going to prioritise. And so what you do is you make sure you've got really, really good methods of dealing with those. And so what we're sharing is good practice as well. So Croydon Group is already meeting. It's been up and running for about a year now. I know that you guys are on it already. So if you're interested in the Croydon Group, no, I'm not going to put it on you. Yeah, Mr. Hargreaves, do you want to just stand up? You're interested? No, okay. The handsome gentleman sitting here in the front. Yeah, if you want to see Mr. Hargreaves, okay, he will talk to you about the Croydon Group and put you in contact with Doug. Okay, and that counts if you're a water company. But if you're a supply chain and you're going, I've got something that would really help customer side leakage, please come and see James. All right, there we go. I know I've gone over, haven't I? I know we are. Fine. We have 3 university projects coming up here today. So we've got Charlie, Luke, and we've got Elizabeth as well, okay? These are important. It's really interesting. I don't go to other conferences where I see PhDs coming up and talking, okay? You don't normally see that at a conference, but you get the PhDs coming up and talking about fundamental research. Why do we have it here? Because of Dunning-Kruger. We know how much we need to learn. We need to understand the fundamentals of why our pipes burst and fail. What's the reasons behind that? What can affect that? And so we embrace this challenge and we get our PhDs up here and they tell us what's going on, or at least what they know so far. So let's start off. Charlie. Charlie, would you like to come on up? He says, looking over there, Charlie. You can tell the PhD because he wears a suit and looks smart in comparison to me. There we go. Grab that. I'm going to sit myself over there for questions in a second.
Hi, I'm Charlie from the University of Sheffield. I'm a PhD student on the YSCDT, currently sponsored by Scottish Water, and today I'm going to be presenting on understanding the impacts of hydrants on transient-based leak detection methods. So just to begin, as everyone here will know, there's a commitment to halve leakage levels by 2050, so it's quite important that we find them. So I'm focused particularly on localization. I think currently the majority of our pipelines are either iron, asbestos cement, or steel. They're known as elastic pipelines, so they're quite rigid. And that means that they're very well suited to acoustic methods. So sound travels quite well along them, so in those pipelines, acoustic methods work really well for leak localization. But we also have increasingly plastic pipelines, which have a bit more of a variable response, which are known as viscoelastic pipelines, so polyethylene, PVC. And one of the things that I'm suggesting is that transient-based methods can fill that gap and help us to locate leakage in these plastic pipelines. So just to quickly go over it, a transient is when you generate a pressure wave through a rapid change in water velocity. So if you have water going through a valve and you close it suddenly, you generate a pressure wave which propagates through the system. I think last year there was a presentation here about the damage that they can cause, and there's been a lot of focus on calm networks. But there is the flip side to that, where if you control them, if you make sure they're below a certain magnitude and a certain threshold, and they're safe, they can be really useful for helping us to locate leakage. So the graph on the bottom there shows, it's slightly hard to make out, but when there isn't a leak in the system, there is a different pressure response to when there is a leak, because you'll get negative pressure reflections, which will sort of take chunks off your pressure waves. So one of the cornerstones of transient-based methods is reflectometry. So it works quite simply like sonar. So you send out a signal which has a certain shape and a certain profile. And if that interacts with a feature, it could be a branch or a leak or a reservoir, you'll get a reflection from that signal back. So the signal sent out is a signal that you get reflected from points of interest, in our case, leakage. So this is an example of the sort of behavior that you see. So the system which I've modeled is shown on the bottom left. It's a simple reservoir pipeline valve system. And in this system, we've generated a transient through closing that valve. The wave will propagate back along the pipeline to the reservoir where there's a constant level of pressure head. So then you'll get a reflection. If you close the valve as a step wave, you'll get a step wave back from the reservoir. But if you have a variable closure, so you close it, open it, and close it again, you'll generate a slightly more complicated transient signal. Apologies, my microphone's dropped off. I might just have to hold it for a second. Let me just use that. Okay. So if you have a closure followed by opening followed by closure, you'll get a more complicated transient signal. And what you can see from the bottom right graph when you have this is that the signal sent out is more complicated, but the reflection that you get back is also complicated. So if this method is dependent on recognizing patterns of transient waves, then it's important to account for that. So people have been looking at transients for 10, 20 years, but they haven't really made inroads in terms of implementation with water companies. I think a key reason for that is that a lot of laboratory work and academic testing to date has focused on generating transients through side discharge valves. So the picture on the left there shows a valve, a side discharge valve. So when that valve is closed, it sends a wave directly into the pipeline. So that's very clean, it's very nice, it behaves well. But in the field, we don't have access to those points. It's more likely that we're going to have access to a hydrant, which is going to act as our point of induction. And in those instances, we're going to have a standpipe with a valve attached to the top of it, more than likely, followed by a hydrant, which again complicates the signal, followed by a connector, which then feeds into the main pipeline. And all of these features will complicate the signal, causing additional reflections, which means that it's harder to recognize the pattern that's coming back because you don't know what's getting sent out in the same way. People in academia have realized that, and they've discouraged the use of hydrants as pressure wave insertion points, which isn't very useful at the moment for transient-based methods because hydrants are the only available points of induction. So before I move on to what I think the solutions could be, I'm just going to sort of elaborate on why it's a problem. So I've got two comparative systems here, but on the left I'm modeling a hydrant induction point, so it's got the standpipe, the hydrant and the connector, and on the right I've just got a side discharge valve, which is more typical of what you'd see in academia. And the pressure wave responses, you can see on the bottom left there, you get a far more complicated signal as soon as you induce a pressure wave at a hydrant. You're going to be getting reflections, a change in the magnitude measured, and importantly, when you zoom in on the leak reflection itself, you see that it's got a very different shape. So hydrants change the outgoing signal and the reflected leak signal. So if we're focused, or this method is dependent on understanding what's getting sent out and what's going to come back, then we need to account for this somehow. So those are the pressure signals. How does this affect leak localization? On the top left is a graph that's the pressure waves, which you saw on the previous slide, generated with a side discharge valve. And if we just take a window of the induced signal and move it across to try and find points of the signal which have the same profile, we find an ideal negative correlation at the leak location. So it's a correlation of -1, which is perfectly negative, which is what we'd expect in an idealized situation, and it coincides perfectly with the leak location. But when we do the same thing with the hydrants and move the red window across and correlate the rest of the signal, first of all, we find it's far more complicated because the red window correlates with itself in a different way. But what's the important takeaway is that at the leak location, we've got a far weaker negative correlation. So if that was masked by noise, it might mean that you wouldn't notice the leak in that case. And also, it's important to note that the maximum negative correlation in this case, which is indicative of a leak, isn't actually occurring where the leak is in the system. And this is all modeled. So hydrants reduce the correlation strength, which is a huge issue when we've got noise in systems, which we always do. And it's also going to reduce our localization accuracy. So is there a solution to this, bearing in mind what I've said before about hydrants currently being the only realistic access points? Well, if we can model the standpipe, the hydrant, and the connector, we can determine how those features would change the shape of the wave as it passes through into the pipeline, and we'd also be able to model how the reflected wave would change as it's reflected back through to the sensor. I've recently had a paper published which has shown that for the connector, so the bit that connects the bottom of the hydrant to the main pipeline, that we can calibrate the properties of those, leading to more accurate leak localization. And we can calibrate those using a pressure sensor on the top of a standpipe. And when I say calibration, I'm talking about calibrating the diameter when it might be unknown, the wave speed when it might be unknown, or the length. But there is a big unknown about the hydrants. Do different hydrants, which are on networks, mainly through bore and screw down, change the transient wave as well? Because if that's the case, it's going to be far more difficult to model because they're all approximately the same length, they're all approximately the same diameter, they're all made of the same material, but they have different internal shapes. So if that is the case, it would suggest that we cannot model them simply. So how have I tested this theory? Well, we've got a laboratory in Sheffield, and there's a schematic on the top right of a simple system. We have a pump which flows water through the system. It flows up through the connector, through the hydrant, through a pneumatic valve, and then back through a hose into the reservoir itself. Each time we control the flow using a flow control device on the end of the valve, and we've generated a transient using a pneumatic valve, which closes in the order of milliseconds. And then we have measured the pressure response at the points which you can see in the red squares. And then we've repeated that with different hydrants. So what do we see? With screw-down hydrants and through-bore hydrants, we get a very different pressure response. We get different magnitudes. We get additional reflections for the screw-down hydrants, which is sort of expected because they're a more complicated shape. It's Yeah, they're vastly different, which would suggest that we cannot model them simply as we would a connector, and they would have an impact in the field on transient-based state localization methods. Another way of looking at this is in the frequency domain. So this is a spectrogram looking at the frequency components of the signal across time, with the yellow areas indicating high energy points. So you can see with a screw-down hydrant, we've got some higher frequencies indicated by the yellow boxes present, especially early on in the signal. And that would somehow have to be accounted for if this was to be a viable method in the field, at least if we were going to model them. So does that mean that this approach isn't going to work, or we're going to have to wait for universal access points? Well, I think universal access points, by the way, would be really beneficial for this as an idea, but they're not here yet. I have worked on a method which automatically accounts for the variability in the reflected waves. So it's not... It's another presentation in itself, really. But it's looking at the repeatability of a signal. That's as brief as I can be. And we've taken that and applied it in the field with Scottish Water. And there's a nice picture on the left of the field setup that we've got. And the early results are quite promising. We injected a transient wave of 1 bar to ensure that we were below the threshold of the pressure rating of the pipeline. And we simulated a leak over 400 meters away on another hydrant by opening it slightly. And through that, we've been able to pinpoint that leak location. Now, I want to stress this is very early on, and there's some more work to do in this area. But it suggests that that change which we see as a result of the connector and the hydrant is not an ultimate impediment to transient-based methods being successful, but further testing is required. So in conclusion, transient-based methods can be successfully implemented if we know the expected reflection shape, or if we have a method which doesn't rely on that. Field implementation currently requires either direct access points to the pipeline, or a method of accounting for the influence of hydrants. But because hydrants are currently the only practical induction points, we need to automatically account for the variability in reflection shapes. So that's the end of my presentation. Thank you for listening.
Charlie, no, because your microphone's not going to work, is it? Because it's now kind of down by your knees. So yeah, stay over there. Okay. I've got a microphone on anyway, so I'll come over to you. That's really interesting. So we've known about this kind of the sonar effect. At the moment, if we're looking for leakage, particularly on plastics, in the past we tend to be passive. It's like, you know, when you think of submarines and they're listening for the sound of the submarine, and then you get the active sonar ping, the other way of doing it. So we've known about that, and we've known that that's coming through as a technology. But that was really fascinating about the effect about hydrants, which I will be absolutely honest was how we were planning on introducing it and showing the kind of problems associated. That last test you did, so tell me a bit more. Material, what was that one that you were using?
PVC, I think.
Do you know the diameter?
50 mil.
So 50 mil PVC, 400 metres, and you were local...
Oh, sorry, do you mean for the Scottish Water one?
Yes, Scottish Water.
Sorry, that was PVC, the diameter was 110 mil, I think.
Okay, 110 mil, so large diameter PVC pipe, you got 400 metres?
Yeah.
Localisation to what level?
Within 5 metres, I think. Okay. But like I say, there's a bit more work.
But it's a starting point as a trial and really interesting in terms of our understanding. Any other questions from the floor? James?
Thank you. Fascinating, Charlie. Thank you for that. I suppose just one question. If we were to use this on scale, is there a risk of creating more leaks?
Interesting question. Yeah, so like I said, last year, I think someone came and, Ed from Sheffield, came and presented on the risks that you get from repeated transients. As I understand it, I had a chat with my supervisor about this, and I'm not aware of the research specifically in this area, but the gist, as far as I get it, is that in plastic pipelines, as long as you are within the threshold pressure limits on a plastic pipeline, it won't cause you too many issues. It might be more of an issue in cast iron and those elastic pipelines I mentioned. But I think it'll be fine in plastic. Obviously, don't take my word for it. There'll be other people who know more than I do.
I think that's more testing required, James. But yeah, we know that from last year's work was looking at cast iron, and that was the micro fractures and things like that. With polyethylene, yeah, it's going to be the cross-linking inside the polyethylene, and that's got to break. I'm looking down at Joe because you're material scientist on this bit. Be the cross-linking, and the threshold for that is going to be a lot higher, I would have suggested, than a 1 bar. Yeah, that would be where we'd have to look at is the joints.
It's also piqued my interest. We use a lot of hydrophones at Anglian, and we don't install them on hydrants. We have a good success rate by not installing them on hydrants. And anecdotally, I think others have less success by installing them on hydrants. I just wondered if there's a branch field here that might look into the correlation between the accuracy of fixed network hydrophones installed on hydrants versus not installed on hydrants, and whether or not any of the deflection. I know it's not creating a propagating signal, but what it is doing is it's receiving the signal from a leak, but maybe the shape and the way that the hydrant interacts with that transient wave can affect the accuracy there as well. So it'd be really interesting if that was a breakaway kind of bit to look at as well. Happy to provide you with a ton of data if you want.
Thanks, James. That's one we'll probably have to pick up later. Charlie, thank you so much. I know we've got to press on, sorry, in terms of time. Thanks, Charlie. Another round of applause, please. Luke is virtual. Okay. Hello, Luke. Nice to see you again.
Hi, Jez.
Luke, I'm going to just say over to you. We can hear you fine. On you go.
Great. So my name's Luke. I'm a third-year PhD student at the University of Southampton, and my project here is the effects on pitting corrosion and fatigue performance of legacy cast iron materials. So we have the next slide, please, and click through once more. Good. So this project focuses on grade 250 plate graphite cast iron, which we say is a representative material of those found in UK water pipelines. Click through, next slide. And lots of these pipelines were managed over a century ago, and with much thicker water thicknesses than actually necessary. So we're trying to look at why are these pipelines lasted for so long, what's actually happening on a microstructural level. Next, please. And then with increases failure in recent years, what is the changing element that's causing these failures to occur? And research preceding this project defined the leak or burst concept. So with small pinhole leaks developed in the pipeline from a surface corrosion pit, which then deteriorates into a more serious failure. So we're looking to explore how these initial pinhole leaks occur, what factors influence initiations, such as soil conditions, the material microstructure, or the corrosion product layers that built up over the years in the ground, and how, if we can determine these factors, can we start to predict where the next failure is likely to come long before it's noticeable from a serious leak. Next slide, please. So, as stated, this is focusing on grade 50 flake graphite cast iron, which is made of 3 key phases that you can see in the image here. So we have perlite, graphite, and ferrite. So the dark grey regions are ferrite regions, the black spots are graphite flakes, and the little light grey is the perlite. So, as a result of the manufacturing process, the microstructure of these materials is extremely stochastic. The size, orientation, and distribution of the phases is random by nature. And the image there is a scanning electron microscope image that's taken of an etched sample. So it's where we can use chemicals to remove the top from the surface of the material and expose the underlying microstructure, which allows us to interrogate these phases. And a large variation in all the phases, particularly the graphite flakes. This is a crucial point, as they can be considered structurally as voids. They effectively provide a stress concentration throughout the material that encourages the initiation and propagation of cracks through the pipeline, and therefore is a huge factor in studying its strength. The next slide, please. So we can start to look at the impacts of this microstructure and mechanical properties. We've done some nano hardness testing. So we indent a polished sample with a nano indenter that's about 4 microns wide, and measure the response of the material. So on the left, we have a map of the polished surface with the indents in. On the right, we have the results of the hardnesses overlaid with the flake structure. And it's quite clear that in the regions where there's more graphite flakes, so the ferrite graphite regions, there's a much lower hardness than those perlite regions with a much higher hardness. This allows us to basically draw there's two regimes in the material. Perlite phases that are mechanically stronger and ferrite phases that are perforated with graphite flakes that are very soft. Go to the next slide, please. So these ferrite graphite regions are incredibly susceptible to corrosion damage, as these two separate phases have a large different electrical activity, which allows these microgalvanic cells to form on the surface when they're exposed to an electrolyte. So on the left, we have some small spots. On the top left, those are pit initiations. They are the very start of a corrosion process on the surface. And as they propagate, that becomes more severe and develops into a uniform corrosion process. So they're effectively the very start of the corrosion career. And they preferentially initiate at the boundary between the different phases and begin to propagate eating through the ferrite, as the ferrite acts as the anode and the graphite acts as the cathode. So to explore these first initiations, we've carried out some potential static pulse testing, quantify the activity of these sites, and understand the potentials at which they begin to initiate and propagate. Next slide, please. We can see here in these graphs, as we increase the potential difference at which we energise the surface, the corrosion current density and therefore the aggressiveness of the surface damage increases at a commensurate rate. However, interestingly, this current density doesn't decrease over time. Just with these initial states, they don't passivate naturally as they would in, say, a carbon steel. They continue to propagate indefinitely, provided there's sufficient oxygen supply to the surface to sustain the reaction. Next slide, please. So as the reaction progresses through the material, you see that this ferrite is eaten away. But as the graphite flakes act as a cathode in the reaction, they remain untouched, leaving behind this residual graphitic structure you can see on the screen, what's also called a topotaxial layer. This layer can trap corrosion products that diffuse up from the corrosion front and compact over time into a coherent film, so a corrosion product film, that begins to restrict the diffusion of oxygen down to the corrosion front and therefore slow the reaction. As time goes on, these layers further compact and dry out and become denser. They effectively act as a barrier, like painting a pipeline, between the remaining material of the pipeline and the electrolyte and the oxygen necessary to sustain the galvanic reaction on the pipeline surface. Go to the next slide, please. So if we look at the crack growth in damaged pipelines, we have pits on this surface that will then soon initiate cracks. We've done a number of damage-tolerant fatigue tests. We take a bend bar sample and we insert a sharp knot into the sample to induce a stress concentration to facilitate a crack in the centre where we can monitor it. We monitor the crack growth rate through the sample to understand the failure mechanisms when a crack is already initiated. Go to the next slide, please. So here on the left, we have some data from my testing. On the right, we have some data from literature that other people have carried out in similar materials in a similar manner. As we see, the data is comparable, and crucially, the point to take is there are very small, stable crack growth regions, a very sharp gradient, and effectively, once a crack is initiated, there's very, very few factors in terms of the material and the microstructure that are actually able to arrest the crack and slow its propagation. Once the material is damaged, it tends to just run into failure. So next slide, please. And part of the reason here is because we have these two separate regimes going on. So here is an SDM image of one of those fractured surfaces. And you can see there's smoother regions and there's quite blocky regions. And basically what we have here is the ferrite graphite fails in a very brittle mode, very brittle manner. This thing is often little in terms of mechanical support to the material, whereas those perlite regions fail in a much more ductile manner. So it can be said that that is what's actually holding together the material. It's a network of these perlite phases interdispersed with the ferrite graphite layers running through. Next slide, please. So instead of sample here, you see a crack growing down from the notch. And as you can see, the crack follows the graphite flakes through the microstructure, jumping flake to flake and minimizing the amount of perlite the crack has to break through. Again, this reinforces the idea that the strength of the pipeline can be directly related to the proportion of perlite present in its microstructure. Next slide, please. As we discussed earlier, another crucial factor is the orientation of these graphite flakes. As you see on the screen, the crack growing down through this sample will be easily able to propagate through this perlite phase. as there's a graphite flake that runs perpendicular to the phase and encourages that crack to split open that perlite phase. The next slide, please. Right. So click once more, please. Here we go. So to conclude, the boundaries between these graphite flakes and the matrix are the crucial factor in understanding the performance of this material. Click through once more. And those on. So from a corrosion point of view, we have these microgalvanic cells with graphite flakes acting as cathodes, ferrite acting as anodes, that begin to propagate indefinitely, with there not being any reaction, anything to restrict the reaction except that corrosion product layer that restricts the oxygen supply. We will see that perlite provides the mechanical strength of the material, forming an intertwined network that holds the material together, with the ferrite graphite regions filling in the gaps. And it's this microstructural variation that drives where these initial pits will be formed, and therefore the likely regions as to where there will be initiations of pinhole leaks. And next slide, please. And once more. So we've observed that the frequency of loading material appears to affect how rapidly this crack propagates in the material. So further testing needs to be done to look into this. We have a number of samples, and ones that you can see on screen, that we've exposed to a salt fog for increasing periods of time to allow a surface roughness to occur and for a coherent corrosion product film to form on that surface. So we can interrogate what is the mechanical impact of these films. And crucially, we'll now be carrying out in situ testing to study the interplay between mechanical loading and the surface chemistry at the same time, while using X-ray, CT, and X-ray diffraction techniques to look at both the three-dimensional microstructure as well as the changing composition of the product film as the test goes on. Next slide, please. So thank you for listening to the presentation, and I'll be happy to take any questions.
Thank you, Luke. So firstly, let me put this in context slightly. So last year we were hearing from the Sheffield PhDs, and they were talking about cast iron, and we were looking at where we get a corrosion pit and how that pit can grow as the pipe flexes as a result of pressure moving through it. And we could see that that was forming, that pit was opening up and cracking. Okay, what Luke has done here is effectively said, okay, how does that corrosion pit start? How are we actually forming that corrosion pit and seeing that effective cell there forming as a result of the different materials? Now, of course, the question is, bear with me a second, Luke, I am getting there, is the so what question. Our cast iron is buried in the ground, yeah? It's the perlite structure of that was decided back in the 1930s when it was cast. So what difference does it make to us that we know if it's a bad bit of cast iron or a good bit of cast iron? Luke, there was a really important bit of finding that you went through there. You talked about the fact that there will be a layer on top that starts to inhibit the growth or starts to inhibit the corrosion. Can you tell us a bit more about that, Luke, this layer that will form that actually stops the corrosion occurring?
Yeah, so as time goes on, obviously you get a corrosion on that surface. You leave behind this residual graphite that will be packed with the product from both the soil and from the reaction beneath it. And this will compact over time and restrict the oxygen supply. Effectively, for a pipeline, kind of the best thing you could do from a corrosion science point of view is leave it. The minute you take that layer off, you're exposing fresh material that will just begin to corrode over and over again, and you're re-exposing that material. What we've found is actually that is what is the corrosion protection, is that product layer film on the surface.
Luke, I'm just going to quote you back. The best thing you can do with that pipe is leave it. Okay?
From a corrosion point of view.
Yeah. From a corrosion point of view, I completely agree with you. But that is killer research for us. This is why we do this kind of stuff. We need to understand what's going on with our pipes and what's causing them to corrode. One of the issues that we have is at the moment, and we've talked about low dig and no dig methodologies, is we dig down, expose that pipe to carry out a repair, and in doing so, we're actually going to start that corrosion happening around our repair and corroding faster in that area, because what we've just done is we've stripped away that surface layer that was preventing corrosion. Or certainly not preventing, but slowing it down. Really important bit of research, Luke. Thank you so much for that. Really interested as well in that structural bit as well. Any other questions for Luke? Right. Luke, can I just give you a second round of applause? Thank you so much.
Thank you.
So we have talked about pipes, but of course it is not just the pipe itself that we're concerned about, but also, yeah, come on up, Elizabeth. It is the environment in which that pipe is laid, okay? The ground around it. And so Elizabeth is going to be taking us through the influence of ground damage.
Thank you.
Over to you.
Thanks, Jeremy. Okay, so just to explain what we're talking about today, influence of ground damage on buried water mains failure. This is in collaboration with some co-workers at the University of Sheffield, and I'm actually going to be talking about 2 projects, so I'll come on to that in a second. So first of all, what do we mean by ground damage? Then I'm going to talk about part 1, it's going to be looking at ground voids, so voids in the ground, and then the second part of the talk is going to be looking at potholes, so damage at the surface. So this is what we mean. We have voids which are next to your pipe, which are the ones that are mostly a problem. And then that's your internal damage. And then you've got potholes, voids at the surface of the ground, which cars may then drive over and then cause potentially something to your pipes beneath the ground. And so this is a 2-part talk on 2 different projects, but they do kind of relate to each other in the end. So the first one is a PhD project that was undertaken by Torfig Elmrom at the University of Sheffield, where he looked at vehicle loading on pipes in the ground where they have got voids next to them, and voids either on top or on the side. And he used what's called a geotechnical centrifuge, which some of you may be familiar with, probably quite a few of you aren't. I'm not going to go into the many complexities of centrifuge modelling, but I'm going to give you a few sort of pointers as to why it's really useful. So basically the idea is you can scale your models down. We can replicate the surface damage from, say, a heavy goods vehicle. We can have many cycles of loading to imagine that you've got many times that vehicle going over the top. We can look at the pipe location. So we've got different depths of pipe, different where the pipe is relative to the wheel laterally as well. And we look at different voids of different sizes. Now, just a little note about centrifuge modelling. That's a geotechnical centrifuge. That's the one in Sheffield. It's a 4-metre diameter machine, which is a medium-y sized one. And it has a payload on one side. That's the tub thing there. So that's for a specific kind of experiment. It's shown with a tub, which is basically for an axisymmetric experiment, like a pile. On the other side is a counterweight. So the whole point is it spins round and it's balanced, in effect. The reason why we bother doing that and we take our soil models and any soil structure, water interaction type problem, and we scale it down and pop it in one of those, is because soil behaviour is fundamentally stress level dependent. If we just take a small scale model and we model it at 1G, normal gravity, then we don't get the right stress level behaviour, and therefore we don't get the right stress strain response of the soil. So in this centrifuge, we can spin our soil up to, from about 10 Gs up to 100. We can actually go to 125, but we tend to stop at about 100 Gs. And that means that we can scale our problems from 10 times smaller to 100 times smaller than in the field. So if we imagine a typical strong box, which is the sort of one that's used in the experiments I'm about to talk about, sort of 600 millimetres by 200 millimetres by 450 in size, that can therefore scale to 6 metres by 2 metres by 4.5 metres, or 60 metres by 20 metres by 45 metres, depending on what we're interested in. So you can actually play around with scaling laws and all the rest of it. And there are some interesting other good reasons for doing centrifuge modelling. You can control the boundary conditions very well. You can basically put your model into in quite small scale condition. You know exactly what's going on because you decide where it's fixed, where it's free. You can measure lots of things. You can put lots of sensors in. You can put cameras in, all sorts of things along your pipe, in the soil, etc., on the boundaries. You can, the other advantage, which I'm not going to talk too much about today, but this is something which I think Jeremy was really talking about, the impact of climate change. This is where it really comes into its own because soil behaviour is a function of the G level, but the diffusion of water through the soil, so pore pressure diffusion problems, consolidation, and flow problems, they go with the square of the G level. So that means you can speed up those processes in a centrifuge by a factor of, say, between a 10 and 100, you're going a factor of 100 to 10,000. And that means that you can look at multiple years of loading from environmental problems like rainfall, heating the soil, rainfall, heating the soil, many, many seasons in the space of about a day, maybe about 10 years in a day. So it's incredibly useful on that side of things. So, and then it's very economical because everything's small. So you can do lots of testing in a relatively short space of time. Okay, so these particular tests, dry fine sand, 0.5 millimetres, dense. Basically, we've got surface loading, as you can see from the top, which was a typical wheel load. The pipe was instrumented with a fixed geometry of about, so replicating 300 millimetres of HDPE. So it was an HDPE pipe. It wasn't breaking and it was empty. So it was just a flexible pipe and seeing what happens when it's in the ground. There were various positions chosen in that red zone there. That's sort of taken from the typical stress bulb you can imagine under a point load in the soil. And things that would vary with the depth of the pipe, the loading, the magnitude of the load, and the size of the void next to the pipe and where it was. This is a sort of the central line of pipes that I've shown in the next picture. I'm actually going to focus really on the bottom one of those, so this one here, because that's the comparator for the rest of the data. So just before I show you that, this is your strong box with kind of a schematic on the left-hand side, just kind of showing where all the different things are. It's relatively simple in terms of its instrumentation because there's no water in this. It's a dry test. So you've just got surface deformation. You've got the pipe itself is highly instrumented, so the deflections of that pipe can be tracked. And because we know the properties of the pipe, because we designed it to be a particular flexural stiffness, then we can determine the bending moments and the shear forces in the pipe. And that's what I'm reporting on today. And just that LP at the bottom that's the definition of LP from the center line, because everything is normalized in the data, in this next data. And this is how it kind of looks at the surface. Once you put your soil in, you put the pipes buried down under there, that's sand on top, and then all the bits and pieces on top to load up the pipe. This is the strain gauged pipe. It's basically strain gauges on either the crown or the springing level of the pipe. And as I said, because you get pipe deformation, you can get bending moment of stress. The pipe length was around about, it was kind of simply supported over 350 millimetres, and then kind of it extended over the edge of that, so you've got a kind of a bending moment that's in sagging and then in hogging over the top of that across about a 6 metre width at field scale for this particular test, which was run at about 20 G. I think it was run about 19 G. The pipe, the voids were constructed of foam. And this is where physical modelling and geotechnics is really good fun, because you have to come up with ways to fake stuff if you want to do it nice and simply. So basically the foam was enough to keep the voids open whilst it was being prepared, but as you spun it up and started loading it, the foam would start to compress and it wouldn't rebound. So it's a simple way to come up with a void of different sizes relative to the pipe. So here's some results of no voids. So in this case you've got, as I mentioned, we're going to look at the case where it's the lowest load, the deepest pipe in terms of it's about 1 metre deep. And then I'm going to, and effectively, depending on how deep it is, you can see that you get a higher load if you're relatively close to the surface. Now that's 0.5 metres, and you've got a 300 millimetre pipe. So it's not that close to the surface compared to some pipes you find in the field. But this is, I say, a normalised bending moment that you're getting there. I will explain this. Effectively, what this shows is the influence of both voids. So on this side, it's voids under. This side, it's voids adjacent. You can see that the y-axis goes down to 150 here and down to 30 here. So obviously, having voids underneath is a lot worse for bending moments coming under your pipe. And in this case, what we've got is the size of the void for the simple case that we started off with. You've got a 0.5 metre diameter void, a 1 metre, no, sorry, not 0.5 metre, sorry, 0.3 diameter, sorry, 0.5 of a diameter, so that's a 150 millimetre equivalent void, 300 millimetre, and then I think 450. So And then the red lines are what happens if you cycle. So as you cycle, it's ratcheting the bending moments up and the settlement down. So cycling is bad news, not surprisingly. And then you've got an equivalent thing with the void at the side, which is obviously nowhere near as bad. There we are. That's sort of the baseline case. Okay, just to conclude, a little bit of information from this PhD shows that for voids adjacent to a pipe, you get bending moments of around about up to 6 times what you found for a no void case at around about 2 diameters, for a pipe depth of about 3D. For voids below the pipes, you end up with a magnitude of about 25 times. You've got a big void. It is just bending into that hole at a normalized, again, quite deep depth of 3 times the diameter of the pipe. Now, these results are only valid for dry dense sand and HDPE of 300 mil. So they're a very specific case study, which is great. It gets us started. But what about clay? What about the water table? What happens if you've got layers of soil or joints or other materials? Or what about if your pipe has got water in it and it's pressurized? None of that's in this. So we're just looking at that simple case, but it does establish a baseline of where we can go from here. So hopefully there'll be some future work, maybe a YCDT. We're putting a proposal in at the moment. Because there's so many things we can do with this. And the second part of the talk I'm going to talk about is a current Acquia project, which is called Understanding Water Infrastructure Risks, Major Bursts, Traffic Volumes, and the Condition of Road Infrastructure. So basically, the upshot is how many major bursts occur in close proximity to big roads and road junctions? Is there an actual link between the traffic and the road condition and those mains? So the whole point of this is to review the evidence, because it's come from some water companies that they think that there is a link, but it could be anecdotal, it could be specific to that company or those companies, etc. So we want to basically take an agnostic view of this and see what the data says. And that's the case, we want to make some recommendations and see what we can do about it. So there's been this noting that you've got these increase in bursts. We know that the roads in the UK have deteriorated over the past several years, and maybe there is a link between them. So pothole produces maybe some sort of water pumping from vehicles, produces some loading, produces traffic jam, lots of water on the road. There's been a fair bit of study, this is just a little bit of literature out there, looking at influence of crossings, looking at speed bumps, and various other things, road deterioration, not perhaps per se, but speed bumps sort of gives you an idea. And there are some ideas about how these things may all relate. So part of this work is to do a lit review to find out what other people have done and see where it fits in with this idea. So our workflow, basic project initiation was in September. Literature review is ongoing. Case studies, they're also ongoing. It's not actually one after the other. We're trying to start those now. And then we're going to look at what's needed in research and undertake a final report. So, the challenges. Okay, so we may think that there's a link between road deterioration and heavy traffic and mains bursts. There's a role of different things. So the geometry and condition of the road and the traffic volume. So these are things outside the purview of the people in this room. But pipe location, burial depth, soil type, soil moisture, that's known by water companies at least to some degree. Pipe geometry, age, condition, etc. We need your data to do this properly. And we have some of the data, and some people have been fantastic. Some companies have given us, already started talking to a number of people about giving us detailed data for case studies. And we also have statistical data from the mains failure database and the attached data pipeline network, which is that thing on the left. So on the right is the official divvying up of the UK into the various water companies. On the left is what we've got out of in GIS. We've just dumped all the pipes that we've taken from the mains non-failure database, the pipe bit, into that. And it takes a very long time to load. But when you get it, you can then match up that to the actual pipe locations, hopefully, and we can see from up to 2018, because that's how long it goes up to, basically what has failed, etc., or have there been where certain pipes of certain sizes and so forth have failed. And that's great, but there is no depth data in that database. And that, for me, is a killer. So not having the depth, having just shown you the previous bit of work, there's a lot of information, material, etc., but there's no depth. And I'm hoping that somebody can tell us in this room, you can maybe tell us how deep your pipes are for different pipes. Maybe you've got that information somewhere and it's not in the database, but it might be in your own database. So what we're hoping is that in order to do this, we can make this a valuable Acquia project, providing information about mitigation and management, about the situation if there is an issue there, but we can't do that unless we have the information from you to actually make sure that we get the best from the project. And that means, in particular, pipe siding, geometry, depth, soil type, all those things here, we need your data. So if you would like to contribute, that would be fantastic if you haven't already told us, because we're obviously talking to a few people. So just to give you a quick who to talk to, there's Torfeg and myself about Torfeg's project. You can also talk to Ed with John. Ed was the guy who talked about corrosion and fatigue and so forth in the last conference. He's now our research associate. He's a kind of pre-doc because he hasn't officially had his thesis examination yet, but he's working on this, and you can either talk to him or myself to give us anything you like or discuss any thoughts you have. So thank you very much.
We've got time for a couple of questions. Yeah, a couple of questions. So thank you for that. That's really, really interesting. So number one, I always look at things like that, and you're starting to put that in context in terms of our mains. And I was thinking about when we're doing a cutout on a piece of pipe. So our issue, so imagine you're doing a repair, you're doing a cutout. Our problem is reinstating underneath that.
Mm-hmm. Yep.
Because we can't get the compaction, because you're compacting from above, and that's already been laid and everything like that. When you were looking at those voids, did you just look at them as completely? I know you were using your sponges, but what happens if you've got some material in there? Does that make much of a difference or not?
Oh, it would. Yeah. I mean, in a sense, say this is a very extreme case. The soil is dense and therefore really good, apart from when there's a hole and it's really bad. So it's a very extreme thing. Yeah. Clearly, in reality, you're going to have maybe some support. Maybe you have a leak in the pipe and that's causing erosion and that's got rid of some of your soil. It might be poor compaction. There's a number of reasons. We haven't looked at more detail on that, but we could look at details where we actually, because, making our own pipes, we can actually have the same problem. If we were to take a piece of pipe out and pop it back into our own models, you're struggling to get the stuff underneath. So in a way, we can mimic a lot of the installation issues that you find. We just haven't done it yet. So there's a whole range of possible things to look at in terms of the construction quality, repairs, and as I said, looking at weather-induced issues as well in conjunction with traffic loading. I mean, they're not separated things in reality. They're on top of each other. Yeah.
Thank you very much for that. Very last bit, I'm just going to put one question out in the room there. Anybody got any ideas on how you can get the depth of your repairs or mains? Anybody?
Valve depth.
Go on.
Valve depth.
Yeah, go.
Valve depth, so you can measure to the top of the valve and understand the height.
Because you'll know the diameter of the valve, and that will give you an idea of that. Certainly for a modern valve, that would probably work as well. Those of you that are working as contractors, is it still practice that you're going to stick a stick up when you're actually doing an excavation to show depth of cover? You may find that in the photos when they're actually doing repairs. Some companies actually require it as part of their health and safety, is they put a stick in to show depth of the excavation as part of what they're doing. If anybody does that.
No, I don't do it. But
right.
And I thought is, do you look at other countries? So Canada, we know they put their mains a lot deeper than we do. Obviously, for other reasons, they do that with their weather. But I'm just wondering, I know it's an Acquia project.
Oh, it's absolutely.
Looking at other countries that we know do deeper mains.
Yeah, no, that's definitely, I mean, what part of the lit review is to, in fact, do that. And we have colleagues at, for example, Queen's in Canada, who do a lot of large-scale testing and have really good links with their water industry. So, yeah, and Australia as well. We have, again, really good links with Monash Uni. So there's yeah, we have a good idea
That's
about
fine.
people like that, yeah.
Joe, very, very quickly.
I was just saying the critical pipe setup we did 10 years ago, they ran 18 truckers.
Mm-hmm. That sounds
Thank you very much. Can we have a round of applause?
Thank you.
To be honest, I'm looking at time. I'm not going to do a roundup apart from saying the following. Don't uncover your pipes, and if you do uncover them, put them back very, very carefully indeed. Bob, over to you.
Well, I'm almost breathless with all that energy that you've generated, Jez. But thanks very much again, Jez, for your chairing that session and all the sparks that have flown off you as usual. And it's great to see these three young people, on the stage today, telling us about their research. I use the word young a bit sort of generally,
I'll take it.
It's great to see Charlie, Luke and Elizabeth presenting that stuff here, and I think it just illustrates to us all the sort of stuff we've got to get into here and the level of detail we've got to get into to understand these mechanisms. Look, I'm slightly conscious that I'm keeping you from the bar, so I'm not going to speak for very long, but just a few announcements for this evening. Firstly, all of the slides and the recordings will be circulated. They'll be on the website next week, so don't worry if you haven't photographed one of the slides, one of the great slides up there. They will be available to you. And just in terms of this evening, the bar through there will be open when we've finished here, and then the pre-conference drinks reception starts at 6:45, is that right? So we'd like to thank Tetra Tech, RPS, who are sponsoring the drinks reception. So thank you to Tetra Tech. Here you are, Joe. Have you got colleagues here, Joe? Put your hands up. Thank you very much. So it's like those guys buying you a drink tonight, okay? Never happened before, is it? So, it's always the first time. Joking, Joe, joking. And then we've got the dinner. We've got a conference dinner at 7:30. So this room is going to be, as if by magic, is going to be converted into the dinner venue. So that'll be back in here. And we've got, for the first time, we've got a sponsor for the dinner as well, which is Horizon Water Infrastructure. I think we've got a slide for that somewhere. And they're a new company to the sector with some new and innovative approaches to funding, smart metering. So you'll hear a little bit from them this evening. They're doing a little presentation at the start of the dinner. So and that dinner starts at 7:30. Have I missed out any other housekeeping sort of related stuff, Judith? The bar closes at midnight, but there's a really good one just down the street, the other side. Joking. So just to summarise today, firstly, thanks to everybody. I mean, I think it's been quite a packed session this afternoon, and you've all been very attentive and very engaged and asked a lot of useful and interesting questions. So thanks to all of you for your support today, but also thanks to Judith and the team for everything that they have done to make this a successful afternoon again. I think there's one thing that I'm just going to say that illustrates the scale of the challenge that's ahead of us. I did talk about that this morning, and that's the fact that you lot have voted 70% to 30% that we're not going to make our leakage target by 2050, which is quite worrying, really. It just illustrates how we need to work together and collaborate much more and do a lot more. So there's much more to be done. You've seen some great illustrations of the sort of lateral thinking that we're now engaged in the industry this afternoon, which is great. You've heard about Ian's proposals to change the way of the leakage measurement methodology. So thank you for announcing that today, Ian, and being happy to take questions. Ian will circulate the answers to those questions that we weren't able to, or we will circulate from Ian afterwards. And thanks also for your positive comments, Ian, about the the fact that this collaboration is growing year after year. So that's important. I think that's illustrated by the attendance here and the support sponsors and so on. So I know Judith has gone, but it's going to be 500 next year, I think, not 200. Oh, she's still there. Next challenge, 500 people. I'm sure we could do it. So yeah, lots of great stuff this afternoon. What else did sort of piqued my imagination? I think the questions that the background leakage presentation, Stuart's presentation, I think for me, you know, the variability of those figures makes me think, hang on, how much do we really understand here? How much do we really understand what's going on in each of these DMAs? We think they're all the same, but actually they are all very different. And those figures illustrate that. That's the one takeaway for me from that. I like Joe's discussion about Formula One and the cross-collaboration on pipelinings. Great to see how that pans out. And we even talked about a secret group, the Croydon group, a secret group in leakage. Well, hopefully not for much longer because we all know about it now. And I'm sure the output of that group will be known to us all in no time at all. So I'm going to stop there. Thanks very much for being a great audience today, and enjoy this evening, and see you all tomorrow morning.